This video is on the PN-Junction Diode. With the PN-Junction Diode, what we mean is we're going to take a piece of semiconductor material and we're going to dope one side with acceptor impurity atoms that have lots of holes in them. The other side we're going to dope with donor impurity atoms that donate a lot of electrons, so we'll have a lot of electrons there. So we're going to talk about the zero bias conditions, by which we mean we're going to apply 0 volts across this device. So what happens then? Well, the first thing that happens is that we have lots of electrons on one side and very few electrons on the other. So electrons are going to tend to diffuse from from regions of high concentration to regions of low concentration. That's diffusion. And here we have lots of holes on the P side and very few holes on the N side, so holes are going to tend to diffuse on over to the N side of the material. Now, what happens now is that the electrons that reach the P side are going to find holes and they're going to combine and neutralize. And holes that leave the P side and enter the N side are going to find electrons and they're going to combine and neutralize. As a result, we'll have a region here in the middle that is depleted of charge carriers, and that's called the depletion region. Now, when these electrons, which carry a negative charge, they leave the N-type material and they enter the P-side material, the P-side material becomes negatively charged. Similarly, when holes leave the P-side material and they enter the N-side material becomes positively charged. So as the process of diffusion continues, we're going to have a built-in voltage and a built-in electric field that is established. So diffusion continues and this voltage will grow to such an extent that at some point it will oppose and stop the diffusion action. And I'm going to remove markers here to make this more clear. Because we see that if we have lots of holes and we have a positive charge on this side, and that positive charge, if it's great enough, it's going to repel further action from holes on the P side. So again, diffusion continues until the built-in voltage is great enough to stop diffusion. So this region that we call the depletion region is the space charge region. It's because it's where all the charge action that we just described happens. So another way of saying this is that leftover electrons in the N side of the material, they will have to overcome this electric field for them to cross to the P side. Similarly, leftover holes is going to have to overcome that electric field to cross on over to the N side. To overcome that electric field, they must attain enough energy to do so. So they need to overcome a barrier energy that is associated with that field. So the depletion width, if we look here at the region that is depleted of charge carriers, if we were to increase the doping concentration of the P side of the material, we have lots of holes here on the P side, and the P side it's more difficult to deplete. So we're going to see that the depletion region and the depletion width in the P side of the material is shorter, is narrower. Similarly, on the N side of the material, if we have higher doping concentration, we have lots of electrons, and that side also becomes more difficult to deplete. So then we see that the depletion width in the N side becomes narrower. So the overall depletion width, which is the depletion width into the P side plus the depletion width into the N side, they actually decrease with higher acceptor impurity atom concentration and higher donor impurity atom concentration. So let us talk about the resulting energy band diagram. So on this side we have doping atoms that donate lots of electrons. So the probability of finding an electron is a lot higher than that of a hole. So the Fermi level is closer, in here we see the Fermi level is closer to the conduction band. On the p side, we have lots of holes, so the probability of finding a hole is much higher, so the Fermi level is closer to the valence band on that side. Now, across the entire material, when there's no voltage across it, the probability of finding charge carriers is equal. So that's why the Fermi level is a straight line across the device that way. And that's how we can connect the two pieces together. But what we see here is we see some band bending. And what that means is that basically any electrons that had enough energy above the energy barrier here, remember here on the energy band diagram, the y direction represents energy. So any high energy electrons were the ones that already diffused over to the p side, and those are the ones that recombined and created this depletion region. So there's nothing here. But as we go below the barrier, then we start seeing more and more electrons. And similarly here, we have holes that they need to overcome a barrier for them to actually cross the junction. So what happens when we put a reverse voltage? And by a reverse voltage, we mean a voltage that reinforces the built-in potential. So what we're going to do here is we're going to put a voltage here, and I'm going to draw it this way. Imagine that we put the voltage here this way, and we want to reinforce the built-in potential, so we're going to do it this way. And that's exactly what we're doing with this reverse voltage here. I just redrew it for more clarity. So this right here is a reverse voltage. Well, what that does, it reinforces the barrier. So now electrons need to overcome an even higher barrier for them to cross the junction. Holes, similarly, will need to overcome a higher barrier to cross the junction. So those dopant carriers are not moving, they're static. In other words, this reverse voltage deactivates dopant carriers. However, we do have on the p side of the material, for example, we do have thermionic electrons. In other words, thermal energy liberates some electrons and places them in the conduction band. Well, now those electrons are going to see a positive charge on the other side, and they're going to be attracted to it, so they're going to cross the junction. Similarly, thermionic holes on the n side are going to see a negative charge on the p side, and they're going to cross. So as a result, we have thermionic carriers crossing. We have a low reverse current. And it is low because the number of charge carriers that thermal energy avails in the presence of a band gap energy needed to break them loose is going to be low. So not a lot of carriers are going to cross. Well, if we take this negative voltage here and we increase it, we're going to reinforce that built-in potential even more. So the barrier is going to be even higher. If we put such a high barrier, basically what we're saying is that now we have a high electric field across the junction. So these thermionic electrons are going to be accelerated to such an extent that their velocity is going to be so high and kinetic energy is going to be so high that when they crash into a bound electron, they can free it. As a result, we free one electron, and we have two electrons after that crashes, and when that electron is freed, it creates a hole on the other side. Then those two electrons are accelerated by the same electric field to such an extent that they crash into two more bound electrons, and they free two more electrons and two more holes. This process continues, and the number of charge carriers that are liberated increases avalanche fashion exponentially, and that creates a current that is significant. So this reverse current becomes very significant when we have a high enough reverse voltage across the junction. What we just described is called impact ionization. Basically is when electrons free other electrons upon impact. And this kind of breakdown, we call it avalanche because the process produces a current that increases avalanche fashion with increasing voltage. And let's remove markers here before we go to the next point. We also have another mechanism that is called Zener tunneling, and that happens when we have a very highly doped junction. So if the P side is very highly doped and the N side is very highly doped, their middle region is very difficult to deplete, and that means that the depletion width here is very short. With such a short depletion width and with a high electric field, what we see is that electrons can be pulled across and tunnel through the depletion region. And this is what we call Zener tunneling. And that's again because the depletion width is so short, which results when we have highly doped P and N type regions. In typical Zener diodes, we have both of these mechanisms happening at the same time. The doping concentration determines which one is more prevalent. Well, what about if we put a forward voltage? Well, if the reverse voltage reinforces the field, a forward voltage opposes the field. So in opposing the field, what we're saying is that we reduce the barrier that charge carriers need to overcome to diffuse and cross the junction. And similarly, we also reduce the barrier that holes need to overcome to diffuse and cross the junction. So what we have here is dopant carriers are crossing the junction. And as a result, then we have a diode current, and a diode current that increases exponentially because as the barrier decreases, an exponentially increasing number of electrons are now do not need to overcome the barrier. So an exponentially increasing number of charge carriers now diffuse and cross both electrons and holes. So as a result, this forward diode current increases exponentially with forward voltage. Now we haven't drawn this here, but this, let me remove markers here. This device is a three-dimensional device. So it actually goes into the board kind of this way. And you can imagine it's just 3 dimensions all the way across. So let me finish this here. So what we're saying here is that if we have a higher cross-section here, we're going to have more electrons. So as we increase that cross-section, we're going to have a higher diode current. So that means that the diode current is proportional to the junction area, the junction between the P and N type regions. So in summary, what we're saying is that the diode current is high only in one direction. So we use a symbol that looks like an arrow, and this arrow indicates the direction of forward current. Forward current when we have a forward voltage that is applied from the positive side of the material to the negative side of the material. On the other side, we have a blocker simply to indicate that reverse current is very low. And for our purposes, is so low that we can say that it's almost negligible, at least for good diodes. So if we look at the IV graph, if we have a diode voltage, a forward diode voltage, and we look at the diode current, we see that the diode current increases exponentially with diode voltage. When the diode voltage reverses and we enter the reverse bias region, we have very low reverse current. It's so low that we can't see it, and it saturates very quickly to the reverse saturation current here. But if the reverse voltage is high enough, we reach the breakdown level at which point the reverse current increases avalanche fashion in the negative direction. So this is how current behaves with respect to voltage. Let's talk about capacitance, and let's remove markers here. We see here that we have a depletion region, that is a region that is depleted of charge carriers. And here we have what amounts to a p-type plate, and here an n-type plate. So we have basically a parallel plate capacitor. That capacitance is a function of a couple of things. And again, we're going to draw the third dimension here. First, the higher the cross-sectional area, the higher the capacitance. So that capacitance is going to be proportional to the junction area. But we also have the distance between the plates. The distance, if it's shorter, we have a more intense field and therefore higher capacitance. We can hold more charges. So when the distance is short, we have more charges, and as a result, capacitance is higher. That's why capacitance is inversely proportional to the separation of the plates. Now we also look at this voltage here. With a forward voltage, when we have a positive voltage here, we're tending to push these holes into the junction, so the edge of the depletion region kind of pushes in, and as a result it decreases the depletion width. And similarly on the N side, when we increase the positive voltage on the P side, it's like decreasing the negative voltage on the N side, and then electrons are going to be pushed away and into the depletion region, so then the depletion region becomes narrower. What we're saying by that is that when we increase the forward voltage, this distance shortens. But increasing the forward voltage is, and let us put here, let's consider with respect to the negative voltage, it's like decreasing the negative voltage. So let us consider the whole thing with a negative voltage. Now, if we have a negative voltage, this negative charge is going to attract holes away from the junction, and it's going to increase the depletion width. And on this side, applying a negative voltage to the P side is like applying a positive voltage to the N side, and that attracts electrons away from the depletion region, thereby increasing the separation. So what we're saying is that the separation increases with reverse voltage. So a higher reverse voltage increases the separation, de-intensifies the electric field, and as a result it decreases capacitance. It just so happens that it goes with the square root. But the main point here is that a higher reverse voltage or a lower forward voltage will decrease depletion capacitance. We also have what we call diffusion capacitance, and let's remove markers here to talk a little bit about that. When we're forward biased, we have holes here that are crossing the junction and reaching the N-type material. Well, holes require time to cross the junction. This is the forward transit time. So at any given time, we're going to see holes in the process of crossing the junction. So what we see here, if you can see here, this is the P-type plate of the P side, and this is the N-type plate of the N side, and holes are crossing the junction, where at any given time we have holes in the middle and in the process of crossing. Well, capacitance is nothing but the ability for a device to hold charge with a voltage, and here what we see is that we have charge in the depletion region, and more specifically we have in-transit charge in the depletion region, and that means that we have effectively a diffusion capacitance that holds that charge. And that charge is basically how much current is going into the junction and the forward transit time that it requires to cross the junction. You remember current is charge over time, so charge over time into the time that it requires to cross the junction gives us the charge held by this diffusion capacitance. When we're forward biased, we have a lot of charges crossing, and the number of those charges are actually going to overwhelm the charges that were held by the depletion capacitance. So diffusion charges are much higher than depletion charges. That means that the diffusion capacitance is much greater than depletion capacitance. Now when we reverse the voltage and we reverse bias, we see that the diffusion charge, basically there are no longer charges diffusing across the junction. So basically those diffusion charges go to zero, and that means that the depletion charge is much greater than the diffusion charge. So when we're reverse bias, it is the depletion capacitance that is much greater than the diffusion capacitance. Something very interesting, and we're going to remove markers here, is when we're in a forward bias condition and we want to go into reverse bias, well, these charges that were in transit are going to stop moving, but in fact we're going to have to pull them back. So there's going to be a momentary reverse current to basically drain this depletion region of diffusion capacitance. So that's what engineers refer to as reverse recovery. Basically, when we recover the reverse bias conditions, we're going to need to pull back and drain all these charges. So that's something to consider, because that requires current, and it also requires time, and that current is flowing in the reverse direction. So reverse current is momentarily very high. I hope this video was helpful. Thanks for watching.